This is William Tomos Edwards from Bright Studies. I want to look at this integral from the MIT integration bee. The YouTube channel Let's Solve Math Problems gave their solution to this integral. They used integration by parts. This is a great use case for integration by parts. I'm going to link to that solution, that video from the Let's Solve Math Problems YouTube channel. You can check that out. But what I want to show here is how we can use a shortcut to take this integral from the MIT integration bee and actually make it trivially easy. This shortcut will not work on the indefinite integral in this case, but for this definite integral from 0 to pi over 2, there's an unbelievable shortcut we can use. Okay, perfect. We've got the answer. There you have it. Pi squared over 8. So to break it down, we can look at this integral. This could be a really tough integral. This could use integration by parts. But on this interval from 0 to pi 2, let's break down how this works. So, and rather than just saying it, I want to look at the thought process of how we might actually use this. So one way to go here, we can say arc sine of cosine of x. Well, the arc sine is an inverse trig function. We're talking about a reverse operation here. So we're going to look at that. We're going to look at the first step here, right? And say, okay, we know it'd be awfully convenient if instead of thinking in terms of cosine of x, if we can think in terms of sine of x. That would be awfully convenient. So let's convert this here to thinking in terms of sine of x. Let's forget about cosine of x. Let's convert this thing in terms of sine of x. Depending on how good you are with your trig identities, you could skip right to that last one. If you're that good with the trig identities, you could skip to that last one. Maybe that's not the way to go. Maybe that's insufficient rigor. And if not, if you don't remember that trig identity, just skip right there. Well, the other thing we can do, frankly, is just do that, right? It's have this intermediate step, right? So you've got the sine of pi over 2 minus x, right? The sine function takes the pi over 2 minus x and thinks it's an angle. It thinks the angle theta. It converts it to a ratio. Then arc sine gets that ratio, converts it back to an angle. It's an inverse operation. It converts it back to pi over 2 minus x. You're going to have to watch out for the indefinite integral because this doesn't work over all intervals. So anyways, so next, we do the inverse operation. We realize it's just pi over 2 minus x, right, is what we're dealing with here. Great. Now we can solve then for that indefinite integral, but I go for another shortcut here. The other shortcut I go for is like, oh, wait a second. This is a linear equation. Okay, this is a linear equation. You're dealing with a triangle. Linear equation means bottom line, you're dealing with triangles in the Cartesian plane. This particular linear equation, plug in 0, you've got y equals pi over 2. Plug in pi over 2, you got y equals 0, x equals pi over 2. And so thus, we can absolutely see what we're going to be dealing with then here for the area of that triangle from 0 to pi over 2. It's going to be pi over 2 squared divided by 2, right? So equals pi over 2 over 8. So that's how we can honestly get the answer here. So, so that's great. There's a way to take that very hard integral and make it trivial. Now, now what I want to get into is why this actually isn't going to work from 0 to infinity or negative infinity to infinity. It's not going to work. I want to just get into that a bit. Okay, so the basic issue is sine has a domain from negative infinity to infinity. Sine can take any angle, any number of rotations. An angle is a rotation. How many rotations have we made? Sine can look at any number of rotations, clockwise or counterclockwise. Sine can take that, whatever it is, 1,000 degrees, whatever. Sine can make sense of it and give the ratio, right? The ratio of the opposite side of the right angle triangle to the hypotenuse, right? But of course, that's restricted. So sine has a restricted range between -1 and 1. For this reason, arc sine has the domain from -1 to 1. But with that said, arc sine has to be an elementary function. So arc sine is not going to map the ratio between -1 and 1. Arc sine is not going to map that ratio back to the infinite amount of angles it could have came from. Arc sine is just going to map it back to an angle in between -pi/2 and pi/2, because every value of sine is included in between -90 degrees, right? The 90-degree rotation clockwise or the 90-degree rotation counterclockwise. Every value of sine is included in that. So arc sine just maps it back to a restricted range of angles from pi/2, from -pi/2 to pi/2. And this creates a situation for arc sine of pi/2 minus x where it does not equal pi/2 minus x over the entire interval. It just equals it on this restricted interval from x is 0 to x equals pi. So that's it. Now, other than that, you get into an infinitely repeating periodic function because it just keeps mapping back to a very restricted range for arc sine. So for that reason, it's not going to, for that reason, the green graph does not match the purple graph.